Okay, so sometimes a two-way table is going to be a little bit confusing, or a Venn diagram. So sometimes we can just make a simple tree diagram to answer the questions at hand. And so this is an example called bags at the airport. So ever since 9/11, there's been a lot of work on making sure that bags are clean and clear so that people are safe when they travel. And so we've got some information. This is some given information for us, so that 5% of bags contain forbidden items. If a bag contains a forbidden item, there's a 98% chance that it triggers an alarm. And if a bag does not contain a forbidden item, there's an 8% chance of triggering an alarm. So we're going to go ahead and start with a tree diagram, and we're going to call this, I'm going to call this forbidden, and this is not forbidden. So the percent chance that it is forbidden, this is 5%, 5% chance. So that means that there's a 95% chance that it's not forbidden. So this would be 0.95, or you can write it as 95%. Now, knowing that, you can now wonder, all right, is this going to trigger, and these Venn diagrams are already drawn for you. I'm just drawing them again so that you can see them. Is this going to trigger the alarm or not? Okay? And we know that if a bag contains a forbidden item, there is a 98% chance that it's going to trigger an alarm. If a bag does not contain, there is an 8% chance that it's going to trigger an alarm. So we can fill in the missing information. Here we know this is 2%, and we know this is going to be 92%, or 0.92. So then, if we now want to know, given a bag contains a forbidden item, what's the probability that does not trigger the alarm? We just multiply these two probabilities together. So given a bag contains a forbidden item, we're going to follow this path here. It has forbidden, but it does not trigger the alarm. So this would be 0.05 times 0.02. And that would be right here, which is 0.001. That is the probability that if it triggers, if it has something foreign or forbidden, it will not trigger the alarm. So that's pretty good chances. So now we want to find the intersection, find the probability that a randomly selected bag contains a forbidden item and triggers the alarm. So this time we're looking for contains a forbidden item and triggers the alarm. So here we're going to do here and here. That's the path we're following. So this would be 0.05 times 0.98. And I think, I can't really read this, but I think this says 0.049. Okay, so that's the probability that somebody's going to come to the airport with a foreign item, or I keep saying foreign, a forbidden item, and trigger the alarm. Here's another example. This is the classic marbles in a bag. So let's go ahead and draw our diagram, our tree diagram. So what you want to do is draw your true diagram of outcomes. So we've got these marbles, and if we're gonna offer a game, and it's 35 cents to play the game. And if you get 2 greens, if you pull 2 greens out of the bag, we'll give you $1. All right. So what's the probability that you're going to win that $1? Well, let's take a look. First of all, you have the option of selecting red or green. That should be AG for green. So the probability that you're going to select red is 2 out of 5. And the probability you're going to select green is 3 out of 5. All right, and you can turn that into a decimal if you want. I'm just going to leave it into a fraction. So now if I choose red, now I've got 1 marble taken out. And what do I have left? Well, I could choose red, and now I've only got 4 marbles left. so it's going to happen 1 out of 4 times. Or I could choose green, and green you can see is going to happen 3 out of 4 times. Please note, you should always be getting 1 when you do this, okay? So let's go ahead and replace that red one, and let's say, for example, that the first marble you chose was green, right? So now you actually have a 50-50 chance of either selecting green or red. This is 2 out of 4, and this is 2 out of 4. But to be a winner, you have to select the path where you go down and you first select a green, and then you select a green again. So you're looking at 3/5 times 2/4. So it's a 6 out of 20 times. So if you play 20 times, you're expected to win the dollar 6 times, right? All right. Another example is being late for school. How many of you are late for school? So think about it. Sometimes you hit snooze, sometimes that alarm just goes off too early. And so we've got this student, Shannon, and she's noticed that she can either hit her alarm, so start with a dot, and you can either hit snooze, or you can decide to wake up. And what we notice is that 60% of the time, she's going to hit snooze. So I'm going to say 0.6 on this one. So that means that obviously 40% of the time, she wakes up. Now from hitting snooze, she's then either late or on time to school. And so in this situation, they said that if she doesn't hit the snooze bar, she's got a 90% probability of being on time. So that means she's going to wake up, she's going to be right here, on time. So that means if she wakes up, she's only got a 10% chance of being late. Now if she does hit the snooze bar, there's only a 70% chance that she makes it on time, which means 30% of the time she's late. So we want to know, on a randomly chosen day, that she hits the snooze bar, on a randomly chosen day, that she's late for class. Well, late occurs here, and it occurs here. So we got to find out these probabilities. And so the probability here, 0.6 times 0.3 equals 0.18. So 18% of the time, she's late and she hits the snooze button. And here, if she wakes up, she's only late 10% of the time. So this is 0.4 times 0.1, which equals 0.04. So that's 4% of the time. So what's the total time that she could be late on this chosen day? Well, you just take these two probabilities and add them up. And so I believe that's 0.22 or 22% of the time. So you calculate each independent and add them up. Now what if I wanted to be more specific? What if I wanted to know what is the probability that given she woke up without the alarm, she's late? And that probability would just be this one right here, this path. Given she woke up and she's late, what's the probability? And that would just be 0.4 times 0.1 or 0.04. Let's look at another example. Let's look at this example in reverse. So now we know that she hit the snooze bar and she's late. What is that probability? So she hit the snooze bar and she's late. So if we look back, she hit snooze and she's late. So that's 0.6 times 0.3, which is going to be 0.18. So 18% of the time, if she's late for school, it's because she hit the snooze button. All right. Another example, go ahead and pause the video. Let's see where you are at this point. See if you can set up your own. I'll go ahead and get you started. you're going to be looking at the probability. So if you wanted to start a diagram here, tree diagram, the two things you're comparing is D and plus. So D is you have the disease. So once you have the disease, what's the probability that you will then be positive, or it was a false positive and you got a negative? And so, sorry, this is disease and not disease. This should be not disease. And again, positive and negative. And so up here, you'll notice that it says that 10% of the population in question has the disease. So we can go ahead and put a 0.10 here, which means you can put a 0.90 here that does not have a disease. So that's this part of the question here. So go back and work it through and see if you can figure it out. Pause the video. All right, and here are the results. We've got a couple more example problems that I'd like you to try on your own. We've got a situation with athletes and drug testing. So again, I would make a tree diagram. And when you read the problem, you'll understand this is going to be a positive and a negative result. And then we're going to talk about, from here, a false positive and a positive. And here we'll get a false positive and a negative. All right? And then when you read through, you should be able to figure out where the numbers go and calculate the probability that you test positive and you actually did the program. So finish that one, and then if you want me to check it, just raise your hand and let me know. And then the second one is these are people that come back to learn their, so this is a rapid HIV test for people that might think that they have AIDS or they want to get tested for AIDS. But because it's such a fast response, it does have a higher increase of not working. This one, you do not have to make a tree diagram. You just have to think, if 200 people are free of the antibiotic and there's a 0.04% chance of getting a false positive, we want to know that the chance of at least one false positive occurring, or how many people are expected to get that. So on that one. And that will be it for right now. If you have any questions, just let me know. Part 3 is coming up.